So today I want to talk about the motions of stars in the Milky Way. Okay, and I believe that this diagram is exactly the one from your text. So the three parts of the Milky Way, they also differ in the way their stars move. So first of all, if we look at the disk stars, the stars in the disk move along circular, slightly undulated orbits, where the stars, they basically stay close to the disk, but they move up and down. But overall, their orbit is circular with this slight undulation up and down, right? And they also all move in essentially the same direction, just like all the planets in the solar system revolve around the sun in the same direction, which is counterclockwise, as one would observe from far above the Earth's North Pole. So the disk stars all move in the same direction. And our sun moves at the speed of about 220 kilometers per second around the galactic center. So you can ask, well, how do we know that, right? We are revolving around the sun. How possibly can we find the speed with which the sun is moving relative to the galactic center? And basically, you determine that from the Doppler shifts of the light that we receive from neighboring stars and different parts of the galaxy. By collecting all these data, you can actually figure out the speed of the sun and us moving around the sun around the galactic center. Okay? So we can determine the orbital speed. We can also determine the distance of the sun and us from the galactic center, which is about 30,000 light years, right? So we know the circumference of the sun's orbit around the galactic center. We know the speed, and from that we can find out how long it takes the sun to orbit around the galactic center once. You simply take the length of the orbit, right, the circumference of the circle, whose radius is about 30,000 light years. You divide it with orbital speed, and then you get the time. And it turns out that it takes sun about 230 million years to revolve once around galactic center. So that's, using scientific notation, that would be 2.3 million is 10 to the 6. Then if I write this 230 is 2.3 times 10 to the second power. Altogether, I have 2.3 times 10 to the 8 years. To put this number into some kind of perspective, most of you have heard or learned that there was a cataclysmic collision between the asteroid and the Earth some 65 million years ago that wiped out, among other things, dinosaurs, right? Until that time, they were the most dominant species on the Earth. But then there was this catastrophic event that channeled the evolution in the favor of mammals, because they were small animals living in underground in burrows covered with fur, and that was advantageous because so much dust was kicked up as a result of that collision that the sunlight was blocked. The conditions of so-called nuclear winter were created. No sun could get to the plants. They died. Dinosaurs didn't have anything to eat. They died out. And also there were severe conditions that there was not usual rain was falling, but acid rain that burned everything, and mammals were able to survive, living in underground in burrows, right? And eventually, through further evolution, became, through us, the most dominant species on Earth, right? So evolution is not something that happens, you know, slowly on and on forever. Every now and then you have these catastrophic events that can channel the evolution in a particular direction. So that happened 65 million years ago, and in that it takes the sun 230 million years to complete one full orbit. Since then, since that catastrophic event, the Earth has traveled only between 1/3 and 1/4 of its way around the galactic center, right? So then you can appreciate how long that period of time is. And we can also, knowing that the sun was formed 4.6 billion years, we can calculate how many times it passed around the galactic center. So that simple calculation, in 4.6 billion, now in scientific notation, billion is 10 to the 9, right? So it's 4.6 times 10 to the 9 years since it was formed. The sun completed. So what do I need to calculate? I need to see how many intervals of time equal to one orbital period, which is 230 million years, or 2.3 times 10 to the 8 years, fits into 4.6 times 10 to the 9 years, and that will give me the number of revolutions. So we have 4.6 times 10 to the 9 years, and I should divide that with 2.3 times 10 to the 8 years per revolution, right? Years drop out, the revolution is going to come on top, so 4.6 over 4, over 2.3 is 2, right? 10 to the 8 over 10 to the 10 to the 9 over 10 to the 8 is 10. So 2 times 10 is 20. So 20 revolutions. So since it was formed 4.6 billion years ago, the sun made 20 complete revolutions around the galactic center. Okay, what about the halo stars? Well, it turns out that while the disk stars move along circular paths, slightly undulated, that the halo stars move in highly elliptical orbits at any angle with respect to the disk, and in random directions. Like these two move this way, this one moves the other way. So in a sense, they resemble bees in the beehive, right? So the halo stars move in random directions along highly elliptical orbits. Okay, so we see that the two groups of stars, those in the disk and those in the halo, also differ in the way in which they move around the galactic center. And finally, the third part, the bulge, basically the motion is similar to the motion of stars in the halo, right? They move along highly elliptical orbits every which way. There is no definite trend like in the disk that all move coherently in the same direction. So all these things, the structure, the composition of the three major parts, the way the stars in those three parts move, would give us hints as to how perhaps a galaxy like our own, the Milky Way, was formed. Now, one can deduce the mass of a galaxy from the orbital data of its stars by applying essentially the third Kepler's law as formulated by Newton, or period, right? Because if you know the orbital period and you know the radius of the orbit, you can figure out the speed, or the other way around. If you know the radius of the orbit and the speed, you can figure out the orbital period, how long it takes a star to revolve around the sun once. Okay, let me just remind you of what is involved. It's really simple. You combine the second Newton's law of motion with his law of gravity, and you can actually see what is the correlation between the mass that is forcing a body to revolve around it and their distance and the orbital speed. So let's just review this quickly. So here we have a central body, say in the case of the solar system it could be Sun, then another body revolving around it, at a distance, okay, let me just draw one more, and that should do it. At a distance d, right, with the orbital speed v. And, of course, there is a force of gravitational attraction that is responsible for this. Okay? So basically what the Newton's second law tells us is that the mass of this body here times its acceleration, and it's accelerating because it's moving along a circular orbit, and its velocity is changing the direction all the time. So the velocity is not constant. And that acceleration, the rate of change in the velocity direction, is caused by the force of gravity. So the Newton's second law tells us that the mass of the body times its acceleration, which for uniform circular motion with the speed v and radius of the orbit d happens to be like this. That must be equal to the force causing that acceleration, force of gravity, which according to the Newton's law of universal gravitation is some constant, gravitational constant, times the product of the masses between two objects over their mutual distance squared. Okay? So what happens here is that the mass of this body that is revolving actually can be cancelled out. I can multiply both sides with 1 power of d, which will eventually remove d from the left-hand side and reduce this power of 2 to 1. And then I can solve this to get the mass of the central object, right? And I get that the mass of the central object is given by a product of the distance between the two objects, the orbital speed squared over a gravitational constant. Okay? So that's how the mass of, say, the Earth is deduced from the knowledge of the orbital data of the Moon, right? We know the distance to the Moon. We can measure its speed from orbital period, and that's how we determine the mass of the Earth. Or this could be a planet revolving around the Sun. Again, from the orbital data of the planet, from its orbital speed and distance from the Sun, it could be measured in principle, we can determine the mass of the Sun, right? Or if this here represents most of the mass in a galaxy, right? So we are looking here at a star moving at the edge of the galactic disk. This would effectively give us the mass contained within the orbit of that particular star, right? Or another way to phrase this is to say that I can solve this for v, and then I get that the orbital speed is related to the distance to the center of the force of gravity. It's basically the root of gravitational constant times the mass of the central object, and then I have to divide with the root of distance. And this is so-called Keplerian rotation curve. And we can apply this to the planets in the solar system, including a dwarf planet, Pluto, right? And you can see that indeed all the planets fall on this curve that represents their orbital speed as a function of the distance from the sun. So this was a great triumph of the Newton's mechanics and his theory of gravitation, that in fact one could explain in great detail how the planets move around the sun. So why don't we try to do the same thing for the galaxy, right? To look at the dependence of orbital velocity of a star in a galaxy on its distance from the galactic center, and basically use this relation here to figure out how much mass is contained in the orbit of the star. And when that was done, there was a big surprise that changed our understanding of the matter in the universe. Okay, they were first measured by American astronomer Vera Rubin in 1970s. So I like to show the pictures of people. She, after finishing her undergraduate studies in physics, she wanted to study astrophysics, astronomy at Princeton. She was not allowed. In fact, women were not allowed to take up astronomy at Princeton until late 70s, until 1977. Okay? So instead she went to Cornell and did very well for herself. Okay, so why are they so different? Let me just show. Okay, so here is a particular galaxy. Catalog number is M33. And you see, you would say, one would argue like this, okay? If we look at the distribution of light, right? The most of the light is coming from galactic center because we have the highest density of stars there in the Bulge and surrounding region. And then as you move away from the galactic center, there's less and less light intensity, right? Because we have fewer and fewer stars. So you would expect that, say, at this distance, anywhere between 5 and 10, this is in kiloparsecs, right? 1 parsec is 3.26 light years, and kiloparsecs is 3.26 thousand light years. So this, the unit here is kiloparsec. So you would expect that, say, at 7 or so, right, that basically most of the mass in the galaxy is exhausted. It's contained within that distance of, say, 7. So you would expect that beyond 7 or so, you would start seeing a Keplerian rotation curve, where the orbital speed actually decreases with distance from the galactic center as a square root of distance. But that is not what is seen. It's essentially slightly rising, and in many cases it's simply flat. Turns out that in our own galaxy, beyond the star, beyond the sun, the orbital speed is flat. It doesn't depend on distance. It doesn't decrease with distance. It's at about 220 kilometers per second, just like the orbital speed of the sun. And that's very puzzling, right? I mean, what's wrong? I mean, are the Newton's laws of motion wrong, right? If you believe that they are correct, what this observation implies is that as you move beyond, say, the visible edge of the galaxy, that there is actually more mass there that you can't see, right? Because look at the relation that we obtained here, right? If this stays constant beyond certain distance, in spite of increasing distance, that means that the mass has to increase with distance. As we go farther away from the galactic center, if this is constant, the mass enclosed within that radius has to go up. But it's not producing any light. So that mass that was initially called missing mass is now called dark matter. We don't know what it is to this day, okay? But if you believe that the law of gravity is correct at these large distances, then there is a mass that is not luminous, that does not produce light, that does not interact with light. But it actually is source of gravitational force, just like any other mass. Then the observed curve is something like this. We have most of the intensity close to the center, and then it decays, right? Because we have most of the stars closer to the center of the galaxy. Now, if we assume that the mass, at least the one that produces light, is distributed in the same way. And here I have a distance from galactic center. So if I assume that just like light, the mass is distributed in the same way, I would expect to get the same bell-shaped curve. So most of the mass is close to the center of the galaxy. But then I would expect that by this distance here, most of the mass is exhausted. Okay? So based on this distribution of mass, my expectation of for what I should see as a rotation curve would be something like this. Beyond this distance, I would expect to get a Keplerian dependence. But that's not what is observed. What is observed is that essentially the rotation speeds remain constant. So as I said, if one accepts the Newtonian gravity, or theory of gravity in general, right, and Newton's laws of motion, then that would imply that there is more mass that we can see. There is also non-luminous mass, or so-called dark matter. And when you do the calculation as to how much mass in addition you have to account for these observed rotation curves, it turns out that typically this dark matter is 5 to 6 times more massive. It contains 5 to 6 times more mass than the luminous mass, the mass contained in the stars.